All right, so last time we were talking about different memory technologies, right? So we kind of talked about that at the high level. We have system RAM, we have hard drives, and hard drives are slower than system RAM. We talked about solid state drives a little bit, how solid state's faster than our mechanical hard drives. And we had a couple of examples where you might use your solid state drive um, for certain things that actually benefit your, I think you were saying you have your operating system on your solid state drive so that when you boot your machine, it's able to load into memory more quickly because the transfer rate and the read time is faster from a solid state drive. So as it's moving that data from your hard drive into system RAM, which all your applications are that's their staging area for getting CPU time is in system RAM. So the faster we can get stuff from wherever their permanent storage is into system RAM, the better. Okay. Some of you maybe have had some experience with this. Have you ever tried to launch a operating system off of an older USB flash drive? So it's nice and convenient, right? Like, oh, I have I have Windows on this, or I have a lot of times it's a Linux distribution or something like that on a USB stick, and it takes forever to launch. Some of the new ones that are USB 3, I mean, those USB sticks are basically solid state drives. They're just smaller capacity solid state drives. So they actually operate significantly quicker. But in general, launching that operating system took several minutes for it to launch. But you carried it around in your pocket. You didn't have to take up your second partition of hard drive space. But now once it was launched, it was pretty quick, right? Once your machine was booted up, unless you had to do something very, very unique that wasn't like part of the core operating system, all that stuff was already loaded into system RAM. Okay, so it might as well have come from the hard drive on your computer at that point in time. So are we wrapping our mind around this idea that no matter where our software starts off being located, when we launch it, whether it's the operating system, Microsoft Word, whatever, it's residing, at least in part, in system memory, okay, in our RAM. So that's where we're operating from, is up there. Okay, and then the relative speed differences between the different types of system RAM is relatively small. That's kind of why last time I think I probably mentioned something along the lines of I wouldn't waste money on the gaming performance RAM. You know, if you have they're not like substantially more expensive, but if you have the extra $30 to just blow, you might as well get the RAM that looks cool, that has the blue heat sinks on it and stuff like that. But, you know, at the end of the day, you know, having a fractionally faster access time is probably not going to be a noticeable thing because that's typically not the bottleneck in your gaming performance. You have plenty of extra time to get data from here to here from system RAM because it's this guy down here that's slowing everything down. Okay? So we want to talk in more detail this time about the various types of system memory. Let's see, did we talk about data? Okay, so we had the slide up last time. So when we think about memory, at the end of the day, what we're thinking about is how do we represent a 0 and a 1? So we could say, how do we represent a 0 or a 1? How long do we need to represent it? All right, so those are kind of two questions that we need to answer when we come up with a memory technology. All right, lots and lots of different memory technologies out there. We're going to talk about the relative high level, kind of two popular ones. Okay, but we do need to answer these things first because these things are important aspects. We can come up with all sorts of different scenarios on how we can represent a single 0 or a single 1. But then we also need to have the idea of, you know, how long does it need to stay? So if we just think about our normal computers, if I were to kill the power on this laptop right now, anything that's currently stored inside of my system RAM, that I have 16 gigs of RAM in this, anything that's stored in there is lost, right? Next time I boot my computer, all that stuff will have to be reloaded into RAM. Some of our modern operating systems, when you shut down the computer, it'll ask you, do you want us to automatically relaunch your applications you currently have open to kind of bring it back to its current state? It is not taking a picture of the current state in memory. Instead, what it's doing is it's just automatically launching those applications for you in memory. What do you think happens when we take our laptop lid and we shut it, go off somewhere, then we open the lid again and it picks up right where we left off? What's actually happening there with respect to memory? Most laptops, what do they call that? Hibernation mode or something like that. What's actually occurring?
It dumps whatever's on your RAM into your hard drive.
Okay.
Like an image of it.
Okay, so it's gonna, the idea is that, like we said last time, typically our hard drive is a lot bigger storage bucket than RAM, right? You know, even within hard drives, he mentioned that his solid state drive is like a 250 gig solid state drive, and his mechanical hard drive is much larger. So, you know, you're gonna pick a spot on your hard drive, and the operating system usually does this for you. It's going to be a spot on your hard drive that it needs to be, you know, at least the same size as your system memory. And it will make a duplicate of your system memory and copy it down to your hard drive. Does that make sense? All right, so that it's prepared to go into hibernation mode. Because when you reopen the laptop, that's when, because when you have your laptop lid closed, you want that to not be using battery life, correct? You know, you shut your laptop lid, you get on a train for 6 hours, you get off the train, you don't want your laptop to be dead. The hope is that, you know, very little battery was drained just as part of the, you know, the normal usage. I know the Macs have the power nap crap on them now, but there's probably some equivalent on Windows 10 to do the same thing where it checks your email and stuff like that if it can. But punchline is you don't want there to be a substantial difference in your battery life. So the idea is as soon as you shut that lid and as soon as we cut electricity to your system RAM, anything that was stored in the system RAM is gone. Okay? Because the answer to how long do we need to represent it in system RAM is as long as there's electricity present. The second we start supplying, we stop supplying electricity to it, it loses everything. Okay, so it's kind of a static charge. As long as power is going to that guy, it can remember, I'm a 0, I'm a 1, I'm a 0, I'm a 1, blah, 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 blah. And then as soon as the power's gone, memory's lost. Okay? We no longer can hold on to that. So before that happens, before we cut the power, we're going to make a duplicate of what's ever in RAM to our hard drive. So that when we open the lid and we come out of hibernation mode, it goes to that place on hard drive and duplicates it back to RAM. Does that make sense? So now, based on what we discussed last time, we'll keep working with his computer. Which hard drive should we dictate the operating system should store that hibernation stuff on? Probably the solid state. Why?
Because it has to boot back up real fast.
Okay, so
You would notice it.
yeah, the longer, the slower the long-term storage is, the longer it'll take to reload that into RAM, right? So it'll take some time to load that back into RAM. Okay, now realistically, what percent of our computer are we using in terms of RAM? So I have 16 gigs of RAM in my computer. How much memory do you think I'm using right now? Let's see, what do I have open? I have a bunch of applications open. 4, 5, 6, something like that. So, you know, less than half of the RAM. So when I shut my laptop lid, is the power immediately going off? Or is there a process? Okay, there's a process where it's having to copy that stuff over. So let's just say that I have 10 gigs of RAM. That's filled, that's being used. So that means I need to copy 10 gigabytes of stuff from my system RAM to my hard drive. Okay? So now we're dealing with, there's two different speed measurements when we talk about memory. One is access time, and then another is data throughput. You know, how fast can we read or write to something? And then how quickly can we access a piece of information? So access time is how fast can we get to the data we want. Read, bandwidth would be how quickly, if we have a gigabyte of data here, how quickly can this guy feed it to us? That makes sense? All right, so let's do some math here. Do you happen to know what the read speed is of your solid state drive? Just faster than your mechanical drive? Okay, so let's do data transfer SSD. There, we'll do verse. This should give us a relative numbers to work off of here. Okay, so here's write speed. And this is kind of what we talked about last time, where the capacity of our hard drives are much faster, or much larger rather, than our solid state drives. So mechanical drives are much larger capacity than solid state drives today. But you see the boot time. Oh yeah, solid state. So typically. Oh, okay, yeah. This threw me off here with the 500 gigabyte thing. So this is saying your standard drives are about 2 terabyte maximum. They actually go a little bit bigger than that now. And they're saying for solid state, they typically are not larger than 1 terabyte. So this is actually probably pretty recent, pretty new information, because 1 terabyte, even today, is a pretty good size solid state drive. You spent some money on that. All right. So when you're booting up your operating system, as you pointed out, he puts his operating system on a solid state drive. He gets a boot time of 10 to 13 seconds-ish compared to 30 or 40 seconds. So substantially faster, 3 times faster, right? Okay. And would you say you experience that? You actually feel that difference?
Oh, yeah.
Okay. So, you know, we can also talk about noise. There's no moving parts with a solid state drive, so you don't hear clicking and that kind of stuff. No vibration, no moving parts. The heat produced, these draw a lot less power. Okay, the solid state drives draw less power anyway, so it costs you less to run them, which means you have longer battery life with them. And with less power coming in means less heat given off, typically. I mean, that makes sense, right? And then, so there's a whole lot of pluses to solid state drives except for maximum capacity and cost, right? And that's the end of the day is you know, if you could have a 4 terabyte solid state drive in your machine and somebody was just going to give it to you and do not charge you anything, you would take it, right? Okay, but if you want to have enough capacity, you got to kind of go with what financially makes some sense. You know, I only really gain benefit from the solid state drive for, you know, these 2 or 3 things. So we look at failure rate. It looks like the solid state drives fail a little bit less often, but you know, those are ballparky similar type of things. But what we're interested in here is this part right here. So write speed for a solid state drive versus a mechanical hard drive. And over these are big B's, megabytes, not megabits. Okay, so this is right in your wheelhouse. All right, I think we're working with bytes here. All right, so we'll just use the 200 number instead of above 200. So 200 megabytes per second is our solid state drives. Over that is let's say what it is. But you know, some of the faster ones, I think the 1 terabyte drive in the new MacBook Pro, I think is 620 megabytes per second. Am I making that up? I think I read that. I think it's 620. Because they also have a 2 terabyte model that's the same thing. So Apple must have, I don't know, bought some SSD company. So everybody else will be coming out with something 10% faster in a week. But in any case, they're a lot faster. So if you look over here at these mechanical drives, they're 50 to 120 megabytes per second, depending on RPMs, right? So if you buy a laptop today with a mechanical hard drive in it, what are some common RPMs you might see when you buy them? Because one interesting thing, if you have a 10,000 RPM mechanical hard drive in a laptop, that's a fire hazard. So
Isn't like 10,000 a standard one for
not standard. Not standard. They exist. 7,200 RPM is usually standard for. That's the faster, because where this hits the consumer is this. Sometimes you'll see for hard drives. So let's say we're dealing with a laptop hard drive. Sometimes a machine will come with a 1 terabyte hard drive, and you can upgrade to a 512 gigabyte hard drive you know, for $200 or something like that. It costs money to cut your capacity in half. And the difference here is that this guy is likely a 5400 RPM drive, where this guy is a 7200 RPM drive. Okay, and where are we going to feel this? That means that this 512 gigabyte drive is going to feel more like a solid state drive than this guy will. It's still going to be slower than a solid state drive. Okay, but the faster the RPMs on a mechanical drive, the faster the read-write time, blah, blah, blah. You get more performance out of it. Okay, so that's where you sometimes will see an uninformed consumer might think that, oh, why shouldn't I have the bigger drive? Well, don't get a 1 terabyte drive if you don't need a 1 terabyte drive. If you can get less capacity, that's enough capacity, that's a higher performance drive, right? It's a higher performance drive. Now you mentioned 10,000 RPM drives. There's also 15,000 RPM mechanical drives that exist, and those look really cool because they have these giant heat sinks on them. Because I mean, you imagine that with moving parts, that thing's giving off some heat, right? Okay, so yeah, I think I had the last gaming machine I built many years ago. I think I had a 250 gigabyte, 10,000 RPM. I think it was a Western Digital Raptor was the name of the drive, serial ATA. And you know, really expensive hard drive. This was probably, I'm guessing that drive was probably like $300 for a 250 gigabyte hard drive, something like that.
When
But,
was this?
huh?
When?
It's got to be maybe 8 years ago. 9 years ago, something like that. Okay, but in any case, so informed consumers are going to understand these performance differences, that everything's not just about capacity. Okay, so let's go back to this guy. So just to keep our, our math, let's say, relatively simple, let's compare the low end of our mechanical drive, so we'll say 50 megabytes per second, compared to our low end of our solid state drive, the 200 megabytes per second. So this is, let's call this the minimum, increase or something like that. So this is probably a 4,800 RPM drive compared to, model 1 year, or model year 1 solid state drives before they got even faster. Okay, so we're going to do our math here. So we said we have 10 gigabytes of RAM to the hard drive that we need to move to the hard drive. All right, so if we're doing this on SSD, we're saying we're going to move at 200 megabytes per second, even though some of the newer ones can go faster, but let's just operate off of that. So how long in seconds will it take to move 10 gigabytes of RAM to a solid state drive? So go ahead and take 2 minutes, do the math, practice your conversions. This could definitely make it onto a final exam. So I want to know the amount of time in seconds it takes to move 10 gigabytes of stuff at 200 megabytes per second. Oh, my wife's earrings got delivered. She better not open that box.
Don't open the box.
I already told her that the other day. Got to get stuff coming.
What's the box? And she's gonna open it and then reseal it.
Okay, so what do we get? 51.2 seconds. So what do? We take 10 gigabytes, so 10 times 1,024, that gets us megabytes. Megabytes. That's like a super vitamin or something. Megabytes, we divide that by 200, we get our 51.2. So 51.2 seconds is the amount of time it will take to move that 10 gigabytes of RAM from your hard drive, or from RAM into your hard drive. And reasonably speaking, about the same amount of time back. We're kind of choosing the slowest of the two units. We assume that our RAM can take stuff at a faster rate than our hard drive could give it at this point. Otherwise, we might as well replace RAM with hard drives. Okay, so our bottleneck here is the hard drive, so we're not even considering access time on the system RAM and stuff. So you can add some fractions of a second onto this this number for overall overhead or something, but we'll call this ballparky. All right, so now when you open up your laptop, does it take 50 seconds for it to come back to life? Remember, this is what the solid state drive. Okay, if we go to our mechanical hard drive, we'll just do HHD, and then we said what? This was 50 megabytes per second, so we can just multiply that guy by 4. So 204.8 seconds. So even with a budget pleaser laptop with a 4,800 RPM mechanical drive, it doesn't take 50 seconds to bring your stuff back into RAM, does it? What's your expectation when you open the lid? How long until you can start using your computer? Negative. That's your expectation. What's your experience?
3 to 5 seconds.
3 to 5 seconds. So soon, quickly, right? Certainly under 10 seconds. Yeah, and in less than 10 seconds, we expect to be off to the races, right? All right. Similarly, when we shut the lid to our laptop, do we kind of assume that it finishes doing whatever it's doing to do the copy stuff relatively quickly, or will we expect that our laptop is still kicking in a minute later? We expect that it's mostly done, right? How do you accomplish that? I mean, it seems obvious that we're not just copying all the stuff all at once, right?
Why couldn't you keep why don't they keep the current state of it in RAM and just have the CPU do nothing while it's closed? Or is that what they do?
Because you cut the electricity. RAM, and this is what we'll discuss this when we talk about the different types of RAM and how we accomplish the different ways of data representation for our hardware. Our system RAM requires electricity to remember. Okay, as soon as we cut the power, we stop draining the battery, but we also stop remembering. So that's the problem solving you have to do with that.
But technically, when you shut your laptop lid, it doesn't cut the power.
Yeah.
It just copies it as a backup, just in case power is lost to your RAM.
It depends. It depends on the type of RAM you have and the type of laptop that you have.
Okay.
Typically, it's going to either cut the power completely, or, especially with the newer laptops that have the whole power nap thing, it's going to drop the power to a point where it barely drains your battery. So some minimalistic, which would be very difficult to maintain system RAM. I mean, system RAM is a power drain. I mean, it does take quite a bit of power to maintain those zeros and ones. So you wouldn't want that draining your battery. You'd want a copy made in hardware. Now, with that in mind, you're kind of a few minutes ahead. We're looking at what's the strategy for doing this. So let's assume for the second that there is no way to remember the stuff in RAM. Okay, let's assume that's the case. All right. So if we're just working with the kind of the puzzle pieces that we know here, when we shut our laptop lid, do we assume it's probably about that same less than 10-second number for when we expect it to power off, whatever? Okay. Well, we've seen that we can't move that much data that quickly. If we're just starting from scratch, do we suspect that it's probably while we're using the laptop, it's probably maintaining that copy of RAM on the hard disk, so that when we do shut the lid, we haven't really lost anything. That's recoverable stuff. We're just kind of keeping those two things synced, right? And it's probably a low priority process that's running in the background because we don't want it, we don't want other things to slow down because we're hard at work syncing our system RAM to our hard drive for something we might not even need. But if we can kind of prepare ahead, for that eventuality of us shutting the laptop lid, that would be good from a performance perspective. Okay, great. So we'll assume we're doing that so that when we do that, when we shut the laptop lid, really what it's doing is it's doing like a last second, confirmation that everything is synced and in good order before we cut the power. Okay. Now, so that's on the way down. Now when we open the lid up, okay, again, if we're assuming that the power is completely cut, okay, memory is an empty husk. Okay, I have 16 gigs of RAM. There's nothing in there. Operating system's gone. Microsoft Word's gone. It's all living in this little section of the hard drive, and now we need to load the entire thing back into system RAM. Okay. Now, Dover said that he doesn't want to wait 50 seconds. He wants to wait -3 seconds. Okay. He wants to be productive before he decides to walk over to the laptop. Okay. It's fine. But certainly less than 10 seconds. Certainly less than 10 seconds. So with that in mind, how does it go the other way? When we're using our laptop, we can be constantly, kind of keeping a piece of the hard drive in sync with our RAM so that when we shut the lid, we have everything saved in a relatively short period of time. But it can't go the other way. When we open that lid, if our RAM is completely empty and we have to load everything back in.
Can you prioritize your data then? Like,
Okay, so we're kind of walking through maybe the history of problem solving this, right? So again, we're operating off this assumption that RAM can't hold any data when there's not electricity. All right, so now we're going to say, oh, well, maybe we decide that certain things are more important than others, like maybe the operating system. So let's get the operating system back in first. And let's say the operating system is 2 gigs of RAM. Okay. Yeah, you're still talking about time. Yeah.
Isn't that what most of them do? Is because what happens is when you open it back up, it takes you to the login screen again most of the time. From when it goes to sleep mode,
that's a setting in your operating system. It has nothing to do with the hibernation side of it.
Well, I was just wondering if they did that for a reason so that they could have time to load everything in.
I doubt it. Yeah, I mean that's an operating system behavior, but so is hibernation. Hibernation is a strategy the operating system takes because it's managing the file system on your hard drive. So it's possible that part of that decision was made because of that, but my gut feeling is probably not. It's probably not related. That's more just a security measure. Like I have my laptop set up to never make me log in. I don't want to deal with the, but from a security perspective, it's probably not smart because I have a lot of stuff on here that I wouldn't want people to access, but I also just don't care. So it is actually kind of funny now that I think about it. Like the number of students I've just handed the laptop to, like at hackathons, to like use for 7 hours, when they could just go into like the Dropbox and like delete all like my consulting projects and stuff. No problem. Just choose to see the best in people, and then you meet Dover.
That's when you start password protecting your laptop.
Start locking your doors. Oh, this happened last week. I found a dog sleeping in my garage.
What did you do to it? Did you cut it up and eat it?
No, he seemed like a nice dog. No, I don't. He wasn't the neighbor dog I don't like. Why his dog seems very nice. I just don't like the neighbor. But I was using my smoker in the garage the night before, and so I opened the garage door like a foot or something like that, so that smoke doesn't billow in my garage. It goes out of the garage. I forgot to close it. So I come out, and I got wildlife in my garage. I mean, who knows what else had been in there? I might have deer in there. Yeah, I'd like to see the.
Some coyotes.
Did you call him Humane Society?
No, he had a collar and stuff. So I called the owner and said, "Your dog is sleeping in my garage," and he said he'd be right over. So it was fine. Yeah. The dog was fine. He was curled up by the hot tub. Everything was fine.
With my car, but
There's no car in my garage. My whole driveway. My driveway is a boat and 2 cars. Garage is golf simulator, big screen TV, hot tub. Who puts cars in a 2-car garage? It doesn't make any sense. There was a logic
People who
there.
don't have hot tubs, I guess.
Huh?
I said people who don't have hot tubs, I guess. But most people that hot tubs have them outside.
People have hot tubs outside. That comes with other requirements. So you don't get the police called on you. All right. So when we reopen our laptop lid, we can't wait 50 seconds for stuff to get copied back to RAM, right? That's not going to fly. So how can we combat this? So one of the things he said is maybe we prioritize. Let's get the stuff that we need first back into memory. Clearly makes sense, right? Clearly makes sense. Now, let's go back here and say, how long has this idea of hibernation actually existed? I mean, we're pretty used to it because it's just kind of the way we use our laptops, right? We're done, you shut the lid, you move on with life. But for a while, when you shut the lid to your laptop, it just shut down your computer. You know, it would try to gracefully shut it down. It would do the normal shutdown process instead of, the hard reset. Like, I'm done, yeah. So it would try to do a graceful shutdown, but it would just shut it down. So really, adding this idea of hibernation was a benefit so that you can just pick up where you left off. How many of you use like the hibernation feature in your laptop all the time? Like you don't remember the last time you shut down your laptop? Huh?
This thing has like the magnetic shut when you close the lid. It does the own lock.
Yeah. But so you don't know the last time it was restarted, right?
It's still practice for me to shut it down. Like after I leave my last class, I do start shut down.
I think I rebooted this recently, so I wonder what this is. Yeah, so this has been up for 5 days, but before that, I bet you it was up really long. So, over the last 5 days, that's a little concerning. So never trust Dover. You don't have a remote into my laptop, do you?
For sure not.
Yes, that was a cackle. I'm sure it's just the two different, probably the root user, because I do some stuff on the root user than the normal user. But in any case, typically we have gotten used to our mobile devices. We use them without shutting them down and rebooting them, right? Until it becomes a problem. So I'm assuming at some point I went months without restarting this thing, and at some point it probably was just acting funky. Something it was zigging when it was should have been zagging, and whatever. I had to actually physically restart it. But we've become reliant on that feature, and that feature hasn't been around for that long. Okay, it's kind of similar to the idea of multitasking in our computers. And even that has to do with memory. Now we have memory, how can we leverage memory to run more than one application at a time? Okay, well now it's like, well, how do I not have to wait to restart my entire computer every single time I want to use my computer? Okay, but now we're back to the boot time. We saw on that example website we were on that it might take 30 or 40 seconds to boot our computer from scratch. Well, is it really a benefit for us if it takes more time to load our last state of memory back into memory? Or would we be better off just rebooting the computer in less time and know that we have a nice fresh version of everything, and the machine should be as stable as it's going to be? That might be the preference. So certainly we're willing to wait less than 10 seconds, probably significantly less than 10 seconds for that to update. So how do we, when we open up our laptop lid and we do the reverse hibernation where we get the stuff back into system RAM, because that's where it's going to be fast, right? We don't want to be operating off of our hard drive. How do we get all that stuff back into RAM quickly? So we mentioned maybe we prioritize. You get some stuff into RAM as quick as possible. How many of you have heard of something called virtual memory? Okay. What is virtual memory? It's the premise of virtual memory as it relates to your computer running in real time with the operating system. It's just one of those things that sounds cool.
It's like using your hard drive as memory, isn't it?
Mm-hmm. So we talk about that in the 350. Anybody in the 350 class right now? Okay, have you talked about virtual memory in there? Okay, so why did I only get one answer from the person who's not in the class? It's garbage. Can't trust anybody these days. That's the problem.
Pretty much.
I had a 4-year-old nephew do that to me at Thanksgiving. This little kid, I look at him, he's like, 4. Kids are monsters. Just monsters. All right, so, you know, what was I even talking about? Oh, monsters. Yeah, kids. All right, so we're not willing to wait for that time, but so we have this virtual memory, and what virtual memory is, it allows us to operate our computer as if we have more memory than we actually do. Okay. This is less of a necessity today because we have lots of memory in our computers, and as you kind of pointed out, if I have 16 gigs of RAM in this computer, I would really have to try to utilize all 16 gigs of RAM, right? Yeah, I'm doing a lot of stuff to use 16 gigs of RAM. All right, you'd have to have virtual machines running and stuff like that to really use up that much RAM under any sort of, you know, even relatively professional level work on your laptop. Okay, but years ago, when you didn't have nearly as much RAM, you might have been operating off of 8 megabytes of RAM, and having 4 megabytes of virtual memory allowed you to be like you had 12 megabytes of RAM, and that could have been a big difference. It might have been the difference of being able to run an application or not run an application, right? But the difference is that virtual memory actually runs in your hard drive. So you're having the slow hard drive, so our slower whatever, you know, now it would be maybe on a solid state drive, but back then it would have been on a slowish mechanical hard drive, pretending to be system RAM, but obviously operating much slower. Okay, it would be kind of like me on the cross-country team. Okay, I'm pretending to be a member of the cross-country team, but they're not relying on me to be the anchor. Is there an anchor in cross-country? Everybody's like everybody's for themselves and just team points. Okay, but you guys know not would be relying on points from me. Probably, right? I mean, like I'm slower than the slowest guy. Okay, and you haven't even seen me run, but you're confident in that answer. All right, yeah, it's terrible. I mean, that's rude, really. So I just call them the way I see them. All right. So, you know, in any case, if we loaded, I mean, we already have this stuff on the hard drive, right? So we already have this idea of virtual memory. We can start getting stuff into real memory by operating off of virtual memory. Have any of you, this is probably less common now, but have over the years of using Hibernation on laptops, have you noticed that when you first open your laptop, you can start doing stuff right away, but sometimes it's a little sluggish? It's not kind of fully up to speed, and you say stuff like, "Oh, my computer just needs to wake up," or it just takes a few minutes to get ready, something like that. It's things that aren't really attributed to computers, right? And it's because for the first little bit, it's operating out of virtual memory. But it's actually not doing anything special related to hibernation. I mean, the way virtual memory works is when we have an interrupt at the CPU, so this is kind of where this class meshes with the operating system class. When the CPU has an interrupt because it needs something, it needs the next line of code. All right, so when you guys have been talking about memory in operating systems, you've probably been talking about paging memory models. All right, so your application that has 100 megabytes of stuff gets split into a whole bunch of pages. Okay, and right now you have page 4 available to you, and at the end of page 4, it's saying, "Oh, I need page 17 now for the next instruction. We're doing a jump to someplace else in the code. I need page 17. We go and look in RAM. We don't find page 17, right? So now we need to go get page 17. So that's when we do a swap. We bring things from virtual memory into real memory. So last time we mentioned this idea that only part of an application actually gets loaded into memory, right? Enough to get started, but then the rest of the application has to get staged in virtual memory so that we can swap those pages into real memory. Okay, so the idea of pages and page frames, those are all operating system concepts, but from our perspective, in here, when we're talking about the different types of memory, we're talking about operating as if it's RAM, but off slower RAM. So the operating system already functions in such a way that if it needs something from real memory that isn't there, it will swap it in from virtual memory. That makes sense? It's slow, it's cumbersome, but it's accurate. So that's why sometimes we would have some of that slow, kind of, getting back, waking up, being kind of sluggish at first, that feeling, because pretty much everything you're going to do for the first couple of minutes is going to have to be swapped in from virtual memory. All right. So this kind of goes hand in hand with what you were saying of maybe trying to prioritize what we need. There might be certain things like the operating system that we need to immediately swap back in. Okay. But then after that, the user dictates what is high priority by saying, oh, I want to do this. Okay, I don't have the page to do that, so let's go find it. And that's when we swap it back in. So that's when you have that kind of that sluggishness, but it still works. So then you can start playing the game of, did I actually gain productivity by having my computer sluggish for the first few minutes as opposed to just relaunching everything from scratch? You know, at some point there was probably a question there. Okay, but now things pretty much get going right off the bat. So something else must be going on. So what do we suspect is actually happening today with our modern memory technology?
Does the hard drive have like a cache memory that's faster than the battery?
That actually does exist in hard drives, and it is leveraged in some ways. So that might be kind of the halvesy solution. You know, maybe we cache some of this, but you know, I mean, just like we've seen with the processors, the cache RAM is going to be a whole lot smaller. You know, if you have a 1 terabyte hard drive, you might have a 4 megabyte cache, something like that. You know, you're not storing a whole lot in there. You know, it's made for like read aheads, stuff like that. So kind of almost pipelining for hard drives, that type of thing. But certainly, those are the type of things we might leverage. But today, we don't really have that sluggishness, right? Typically, if we have that sluggishness when we first turn our computer on, that kind of gives us an idea that maybe our computer has outlived its welcome. You know, it's maybe just a little bit too slow to run the software I have on there, that kind of thing. And that happens. You know, at some point, you just got to get a new machine. But generally speaking, if you have a new computer today, or a new-ish computer today, and you open it up from being in sleep mode or whatever, it's good to go, right? Within a couple of seconds, everything's just back to normal. So what does that imply about how the memory, the actual system RAM in that guy, must work? So it gets back to this question right here. How long do we have to actually represent our values? Typically, when we think about system RAM, we're thinking about representing the values on a very temporary, well, very temporary, that's probably the wrong word, you know, on a somewhat temporary basis, as long as there's electricity applied to it. You know, we would probably say things that are very temporary storage are like registers, right? I mean, registers are going to change. The value that's stored inside of a register is going to change on a per clock cycle basis, potentially. So, you know, that's going to be very, very volatile. But with our system RAM, the historical nature of this RAM is that we want it to hold data for as long as there's electricity applied to it. Okay. Well, now we're going to say, you know what? When I shut my lid, I want the electricity to go away because I want my battery life to persist. But at the same time, it would be in our best interest not to lose the data that was in that RAM because it takes too long to copy it back in. That make sense? So what do we do? What does the way our laptops seemingly work today imply about our system RAM today?
There's more of it, so we don't have to do as much loading. It's faster. All the above.
Okay, yeah, well, it's faster than it was 2 years ago and 5 years ago and 10 years ago, sure. By us having more probably means there's more to load. Our hard drives aren't necessarily substantially faster minus SSD type drives, but the fact that we don't feel like we're having to wait at all probably means that we're not really doing a copy from the hard drive to system RAM. It's happening faster than we could copy even at the super fast SSD 600 megabytes per second, or if we want a 4800 megabit per second over, just for your records.
Is there another staging area then, besides the hard drive?
Well, in a matter of speaking, maybe. I mean, I don't know. The part of that is the another staging area. It's the issues. When we say that system RAM is temporary storage as long as there's electricity applied to it. So now we're starting to talk about the nature of that technology, how the data is represented in system RAM. Okay. Now I'm telling you that electricity is required to remember it. Okay, this is back to our data representation. I need to remember a single 0 or a single 1. And, obviously, when we're storing a lot of stuff, we need to remember a lot of zeros and a lot of 1s. But at the microscopic level, let's say, okay, at the circuitry level, we're storing a single 0 or a single 1, and the technology that our system RAM uses is a technology that requires electricity to maintain that state. Okay? Now, we're suspecting that when we shut that laptop lid, that our system RAM is not just going blank. If it was going blank and we were having to refill it, it would take too long. It doesn't appear to be what's happening based on our experience using our laptops. Okay? Which means that somehow it's maintaining the value in there. Okay? Our RAM is turning into persistent memory. All right, so now you mentioned, well, I said you were a couple minutes ahead of us here with something you said earlier. So would we all agree that one of our goals is when we shut our laptop lid that we don't want our battery to die on us, right? So that's the truth. So we would at very least like to minimize the amount of electricity that's being used. Let's keep it on the bare minimum of whatever needs to happen to do its thing. I always thought it was funny with those laptops that have the little light on the front that when it's in sleep mode, the light still flashes on and off. You seen those? You know what I'm talking about? Why waste it on that? You find it's an LED, it's not using very much, but why? Every little bit counts, right? It just seems stupid. Okay, but there's your evidence that there's some electricity going on somewhere in there. Right? So might there be, and we'll have some time here in a minute or two to actually talk about the nature of that RAM a little bit, but might there be kind of two different modes that our RAM can be in? Kind of an active state mode where we're like prepped for people reading and writing to me in real time, where we need to be kind of more nimble versus a bare minimum amount of electricity that is just enough to not forget, with the understanding that nobody's modifying me. I don't need to have all these extra checks and balances in place for people modifying parts of memory and stuff because the laptop lid is shut. Memory's not changing, right? All right, so we go in here to our memory breakdown. So we have a couple of different memory models here, and we kind of talked about this last time, SRAM versus DRAM, just at the very high level. So here's the generalistic difference between these two. So SRAM is simply integrated circuits that are memory arrays, usually single access ports that could provide either a read or a write. They have fixed access time to any datum through the read and write access time. The read and write access times may differ. These kind of sound like our registers to us. If we scroll up here, we see the access time of our SRAM. Very, 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 very small. Very quick, right? Okay. Sounds like registry type stuff. Okay. Probably not our system RAM stuff, especially when we look at the dollars over here. Okay, so
that's per
gigabyte. Yeah. So this is pretty, and that's in 2012. It's come down in price even more than that. Okay, so then we get to DRAM stuff, and we've probably even seen that when we when you buy RAM for your computer. It might be called like SDRAM or DDR3. Well, DDR3 is usually DDR3 system RAM. What's the DDR for graphics cards? Is it DDR5 for graphics cards? Yeah, whatever. But those are all DRAMs. Okay, all those guys share the technology. They all share the same technology. So let's go look at the DRAM thing here. Okay, in SRAM, as long as power is applied, the value can be kept indefinitely, like we've already said, right? As long as we got electricity there, we can maintain that power. In a dynamic RAM, DRAM, the value kept in a cell is stored as a charge in a capacitor. All right, so a capacitor is like, think of it almost like a mini battery. So it's a little circuity thing, and you put power into it, and it kind of fills up like a water tower. Okay, so you think about it, once it kind of hits its capacity, it sits there. All right, it doesn't take any more, but it can be drained. All right, so it keeps that stuff there, and as long as the capacitor maintains its charge, we haven't lost any data. Okay, this is going to be an important part to understand what we've just been spending some time talking about. All right, let's see. A single transistor is then used to access the stored charge, either to read the value or to overwrite the charge stored there. Okay, overwriting the charge might mean draining the capacitor to store a zero. Because DRAMs use only a single transistor per bit of storage, they are much denser and cheaper per bit than SRAM. Right? So when we talk about SRAM, you'll see that because there has to be all this error checking, there's constant electricity, we actually use like 7 transistors to maintain this one value, because if we read from this value, we don't want to lose that value, so these other transistors have to maintain that state. Okay, kind of think about like we were watching Star Wars and the dudes are doing the lightning shooting stuff, and like Yoda's holding up like a big rock, but he can get distracted, but the rock starts falling a little bit, but then he has to like put the more, because Yoda's got multiple streams of transistors. You get what I'm saying, right? We were talking about Yoda. Because I love Yoda fight scenes. Those are just great. Especially when he comes in a little cane. He's just force pushing off the wall and stuff. What does a guy like that need a cane for? Thinks we're all stupid. All right. So, in any case, this is why DRAM is so much less expensive. It's because it takes so much less room in order to maintain a single bit. We only need one transistor to maintain 1 bit of dynamic RAM. All right, but now we're getting back to this thing about how does that thing maintain its value if we remove the electricity? And that's where the capacitor comes in. All right, so the capacitor, let me show you a picture of these dudes. Capacitor. Images.
We get when you bring it in and make it explode.
These dudes, okay, something that looks like this, except that here's a whole collection of capacitors. All right, so the idea is that these things, usually it's just a diode, so it usually is 2 inputs. These are kind of fancier type things. But one of these is a positive, one of these is a negative. Power goes in, gets stored. Think of the capacitor, this top thing. Think of this like a water tower. Okay, it gets filled up with energy, and then the energy will drain out on its own over time. Okay, it does not hold the energy indefinitely, but it does maintain that energy for a good amount of time, as long as a level of electricity is applied to this every so often. Let's say, kind of, the water tower drains a little bit, fill it back up. Drains a little bit, fill it back up. That kind of thing. Does that make sense? So we can intermittently redeliver electricity to our capacitors to maintain the values that are currently in them based on the current state of the transistor. So remember, we talked about transistors, and transistors are only there's a switch, an on or off switch. So if we put power to a transistor that's currently in its on state, power would flow to the capacitor, right? If we put power to a transistor that's currently in its off state, it's not going to flow through. So that capacitor is not going to get any energy. So a capacitor that was already empty will not refill, because it shouldn't be filled, because the transistor doesn't have a completed circuit. That makes sense? So zeros, it's easy to keep zeros. It takes no electricity to keep a zero a zero. Okay, it takes electricity to make ones stay ones, is the idea here. Okay?
But doesn't it still take power to show 0? Because I thought it was anything less than 50%. Is that still fine? No. The whole.
Oh, it's anything less than 50% would be read as a 0. Yeah, but so as no value is less than 50%. So yeah, that's a hard 0. when that capacitor is completely drained, that's a hard 0. So yeah, we can take advantage of the fact that we don't need energy to maintain a 0. We do need energy to maintain a 1, but using a capacitor is going to give us the flexibility of not having to provide constant energy to maintain the 1. All right, because we'll have to be working with the drain rate of the capacitors. And the larger the capacitor, the slower it drains, right? You can get these big honking capacitors. Yeah, I mean, you can imagine this guy's a lot bigger than those other ones, right? So chances are you fill that guy up with power, he's going to be able to hold 0 or 1. He's going to stay above half full for some time, right? Yeah, so my buddies and I, we used to work with some robotic stuff when I was younger, and then you get a bunch of guys together and IQs drop. We always thought it'd be fun to charge a capacitor and then put on your tongue. It's a bad idea, especially when you deal with large ones. Okay, because this guy, I don't know if you can see on some of these, but like this is probably, yeah, this one is like this one right here. So not even the biggest guy. Well, I mean, that's 16 volts. I mean, 16 volts will power some stuff.
Just think about doing a 9-volt battery.
Yeah, so it's, yeah. But in any case, so don't do that. But I haven't worked with electronic stuff in years because my tremors and soldering is a problem. Last time I tried to solder, because soldering is very precise, right? You're supposed to get the little drop of solder, the melted metal on something, let it cool off, and it seals there. Well, I am just having blobs all over the place. I'm flopping all over, and I'm left-handed, and I can't solder with my right hand for some reason. And that's my steadier hand, which I would call unsteady. Okay, this hand is not, it's barely a functional hand, is what it comes down to. So I rely on my current electronics. Any of you know Steve Caruso in the department? Yeah, he's pretty big into electronics. He's my solder guy. So he fixed the hoverboard.
Oh, really?
Yeah. He opened that thing up, and apparently there was whatever was making the other ones explode just melted a wire. And you know how they won't let hoverboards on like airplanes and stuff because they kept exploding? Well, this was like a higher end hoverboard, so apparently the thing that usually would have made it explode just melted a wire. So he soldered on a higher gauge wire. So yeah, we should be good to go with that thing again. All right, but in any case, these capacitors hold a charge for a period of time. You can think of them for us in here almost like a battery. Okay, and a battery will drain over time. Okay, batteries will drain more slowly than capacitors. Capacitors do drain significantly more quickly than batteries, but they drain way, way, way less quickly than if you have no capacitor and just cut the power. Okay, no capacitor and take away electricity, drained instantly. Capacitor, take away electricity, slow drip to empty. Okay, so that means if we're using a technology that is reliant on a transistor plus a capacitor, a single transistor plus a capacitor to maintain a single 0 or 1, and you can figure that you can miniaturize those things, we have to play this trade-off. We can create RAM that could hold a state for longer periods of time if we use bigger capacitors, right? But if you use bigger capacitors, then you need to get bigger size. So all of a sudden, your laptop becomes 6 times the size that it was before, and you extend your battery life by 20% because you don't even have to provide any power to it as long as you use your battery. You open up the lid within the next week or something like that. Because each capacitor is each capacitor is basically a miniaturized car battery, is what it comes down to. All right, so that's kind of the generalistic pitch on what DRAM is. It's a single transistor plus a single capacitor, relatively small capacity capacitor for maintaining a single 0 or 1, where when we remove electricity from the equation, it drains not instant. Well, it does not drain instantly. So that means we can maintain that by giving it a level of electricity at some point in time.
Would the capacitor be on the stick itself? Or
Oh yeah, on a per bit basis. Every single 0 or 1 that we need to remember takes a transistor plus a capacitor. Yeah. So, if you imagine 16 gigabytes, so that's 16 times. let's see, 16 times 8 would be gigabits, 128, right? Times 1024 is megabits, times 1024 is kilobits, times 1024 is bits. So 16 gigs of RAM would take what's 137 trillion 430 no 137 million no billion 137 billion 438 million 953,472 transistors and complementary capacitors. Okay, so we have to get 137 billion transistors into a stick that big. Actually, we need to get half of that because usually 16 gigs of RAM is stored as two 8 gig sticks. They do make 16 gigabyte sticks, but it's usually an 8 gigabyte stick. So 70 billion transistors on a single 8 gigabyte stick. So that's miniaturization for you, right? Okay, you wouldn't want to prototype that. Especially not with me with a soldering iron. Almost one little spot, the whole RAM chip is dead. All right. We're 25, right? Still got 5 minutes. We're good. Okay. All right. So we have a general idea of how DRAM kind of works. All right. Now, what's nice about DRAM, and I'm going to give you a relatively short homework assignment, doing some problems related to DRAM here, so you'll learn more about it from there. But what's nice about it, I've kind of given you a hint on the SRAM side of things, where SRAM is significantly higher performance because it is relying on a constant power supply and reading from a direct connection versus reading from a capacitor is faster. Okay, because a capacitor, you kind of have to sample from the capacitor to get a reading, to get an output voltage, where reading a direct thing is much more, it's much closer to direct digital. It's either on or off, whether or not there's a zap or not. Okay, but with a capacitor, well, okay, now I'm getting a little ahead of myself here. With SRAM, like a register that requires electricity to maintain its state. Okay, with that guy, when there's electricity applied to it, and I read from it, it's either on or off. Okay, but we have a series, like I kind of mentioned that in most technologies, it's 7 transistors, all working in tandem to maintain a single 0 or a 1. Okay, so imagine if we had a 16 gigs of RAM represented as SRAM instead of DRAM. We don't need any capacitors to make it work. You also lose your hibernation ability. Okay, but we're going to get some good speed out. Okay, but that's a lot of transistors in in a very small space, giving off a lot of heat in order to maintain that. But every single time we read from SRAM, every time we read from that, we drain the energy. We're taking it away. But we need to remember that guy used to be a 1, because when we read from that transistor, that value, that 1 is now gone. That's why we have 6 backups to rewrite it. Yeah, we're zapping it. So we need to have backups to maintain that value, because when we read, somebody else isn't able to read for some fraction of a fraction of a fraction of a second. This is all happening in kind of subhuman time, right? We're not really experiencing that, but you might have 2 different applications that try to read from a single SRAM at the same time, potentially, right? Especially in multi-core type setups that are, well, it wouldn't be multi-core, it would be multi-threaded setups operating on a single core, where you might try to read from the AX register, let's say, at relatively the same time. So technically, you'd only have 2 instructions read from the register. You can only have 1 instruction read from the register at the same time. But if this instruction reads from the register, and then this instruction then goes and reads from that register before the register has recovered from the previous read, you'll get a bad read. Your data is lost. Does that make sense? There's this weird balancing act. So there's a lot more parts to maintaining that value to keep that speed up, which is why it costs so much more per megabyte or byte, however you want to end up measuring it. That makes some sense? All right, so that's kind of our DRAM technology, and that can come in lots of different, kind of forms. So you can imagine taking this baseline DRAM and say, okay, well, I want the RAM to last longer, or I want the RAM doesn't have to last as long without electricity, just because the nature of how we're using it. Maybe it's electricity that you only want to stay alive when there's power coming to it. Well, at that point you say, well, I really want it to act kind of like SRAM, okay, but I don't want to pay for an SRAM implementation. So at that point you reduce your costs to make it by using smaller capacitors. The smaller the capacitor, the longer or the shorter the lifespan will be of the value. But by using smaller capacitors, you also reduce the cost, because you can imagine that a bigger capacitor has a bigger cost and also a bigger footprint. So you can make a pretty miniaturized RAM chip, even with just normal capacitors. Just a human being making a prototype for this, if you use very, very small capacitors with your transistors to store singles, zeros, or ones, and that's relatively inexpensive on a per bit basis. So you can make very cheap RAM that doesn't have to have the performance benefits of, we're not talking about speed, we're talking about the ability to maintain a value over periods of time. Make some sense? All right, so what I'll do is I'll go to the end of this chapter here. I'll probably pick about 3 questions, okay? Specifically dealing with DRAM. I'll probably pick 3 that deal with DRAM, and then I'll probably pick 1 starter question for SRAM. All right, and that'll be due on Tuesday. All right, so I'll put them up on Blackboard here in a little bit.